temperature distribution across a wall of a 1 meter thick at a certain instant of time is given as this function. T as a function of x is equal to a plus bx plus cx squared, where t is in degrees Celsius and x is in meters, while our a is equal to 900 degrees Celsius, b is equal to negative 300 degrees Celsius per meter, and c is equal to negative 500 degrees Celsius per square meter. A uniform heat generation given by G is equal to 1000 watts per square meter is present in the wall of area 10 square meter. Having the properties rho is equal to 1600 kilogram per cubic meter and K is equal to the thermal conductivity is equal to 4 watts per meter K, and the specific heat is 4 kilojoule per kilogram K. So let us determine the rate of heat transfer entering the wall or at x is equal to 0, and the rate of heat transfer leaving the wall when at the x is equal to 1 meter. Okay. So for requirement number 1, let us have some illustration first. So say this is our wall with this is our wall. So this is our boundary. Length of this wall is 1 meter, right? So we have 1 meter from x is equal to 0 to x is equal to 1 meter. Okay. Say this point is at 0 and say this point is at 1 meter. Okay. There is a heat generation G, which is equal to 1000 watts per cubic meter, and we also have the stored energy, and what else, and some given properties. Say our K is equal to 40 watts per meter K. What else? The rho is equal to 1600 kilogram per cubic meter, or the density. The Cp is equal to 4 kilojoule per kilogram K, and the uh, the uh, the time at a certain instant is given by the function t as a function of this position x is equal to a plus bx plus cx squared, wherein the values of a, b, and c, where a is equal to 900 degrees Celsius, b is equal to negative 300 degrees Celsius per meter, and c is equal to negative 500 degrees Celsius per square meter. Okay. So what else do we need? What else? Okay. Ayun. The area is the area. Yan. The area is equal to 10 square meter. And what else? I think that's all. So let us now solve the problem 1. So for the solution, for the number 1, we need to determine the rate of heat transfer entering the wall and leaving the wall at x is equal to 1 meter. Okay, let us first say designate some uh, names of our Q, like let's say let our heat transfer at when x is equal to 0, so at this position. So we have rate of heat transfer entering, and let's call our rate of heat transfer leaving Q at x is equal to 1 meter, right? So this is the rate of heat transfer leaving. Okay. So for the solution, we need to find these Q when our x at this instant, and then our heat transfer at this moment when x is 1 meter. Okay. So first, for the Q when x is at 0, and we can also always use the general equation, which is K A, our uh, delta T per delta T delta X, as from x is equal to 0. Okay, so the value of our K is 40 watts per meter K, 40 watts per meter K, and the area is 10 square meter, then dt dx. Okay, so we need to solve for this term. Okay, to find the derivative of t with respect to x, to find dt with respect to x, we need to differentiate our given function, right? Need to differentiate this. So our given function is t of x is equal to a plus bx plus cx squared. Okay, when we differentiate it, we can now have dt over dx is equal to the derivative of the constant is 0, the derivative of bx is just b, plus the derivative of this term is 2cx, right? So we can now have this new equation. So say this is our equation 2 and this is our equation 1. Okay. So when since we need to determine the Q when x is equal to 0, so we can now solve for the value of our uh, uh, dt over dx when x is equal to 0. So our derivative with respect to x is just the value of b is given, which is negative 300 degrees C per meter, right? Let's check. Yeah, it's negative 300 degrees C per meter, then plus 2, then the value of our C is negative 500. I mean this is 50, sorry, so this is only 50 degrees C per square meter. and then when x is 0, so that is 0. Okay, so this term will be cancelled out. Then the uh, the partial derivative of t with respect to x when x is equal to 0 is equal to 300 degrees C per meter. Okay. Okay. So from equation 1, we can now substitute the value of our dt to solve for our q when um, x is equal to 0. So using equation 1, using equation 1, q is equal to 40 watts per meter K multiplied by our area, 10 square meter, and this derivative is negative 300 degrees C per meter. Okay. Therefore, when x is equal to 0, or in this position or at this instant, the value of our Q, or the rate of heat transfer, is equal to 120,000 watts. Okay. Okay. So to solve for the value of our Q, leaving that is when our x is equal to 1 meter. So we also need to determine our dt over dx when x is equal to 1. Okay? So from here, when x is equal to 1 meter, then our dt over dx is equal to 300 C per meter plus our 2. Then our C is negative 50 C per square meter multiplied by, instead of 0, we will use 1 now. Okay. Therefore, dt dx is equal to, when x is equal to 1, it's now equal to negative 400 C per meter. Okay. So this is dt over dx when x is equal to 1. Okay. Therefore, using equation 1 also, this can also be applied, because q at x is equal to 1 is just the same as ka dt dx when x is equal to 1, or our k is 40, a is 10, and dt dx when x is equal to 1. So this is 1. So using this equation, and you can now substitute the value of this partial derivative of t with respect to x when x is equal to 0 here. Okay. Then our q at when x is equal to 1 meter is just equal to 40 times 10 times negative 400 is equal to 1600 watts. So this is our Q at x is equal to 1 meter.